Alright, hi guys. So here's a lesson, a reminder about isotopes and average atomic mass. So how do we account for the different isotopes of each element on the periodic table? So what we figured out is that we have a mass for individual atoms, but we have different isotopes. So for each element on the periodic table, it has a unique mass because they have a different number of protons and neutrons. We ignore electrons because electrons weigh 1,000 times less, so they're negligible. But based on the number of protons and neutrons that any given atom has, its mass is going to be different. And each element can have many different isotopes. So underneath here, I have H1, H2, and H3, which means that H1 has 1 proton and 1 electron. H2 has 1 proton and 1 neutron, and that's what gives it a mass of 2. The proton weighs essentially 1, and the proton and neutron each weigh 1. So if I have a proton and a neutron, that weighs 2. And then for hydrogen 3 over here, I have 1 proton and 2 neutrons. If you remember, the number of protons makes it hydrogen, and the number of neutrons changes its mass. And then the number of electrons makes it neutral. So I have 1 proton, 1 electron, 1 proton, 1 electron, 1 proton, 1 electron, but the number of neutrons is different. And we can see down here that they have different abundances. So this is like the amount of hydrogen of each isotope that I have just in the world. So you can see that most of it, 99.98% of hydrogen is hydrogen 1, and that a little bit is hydrogen 2, and that hydrogen 3 exists, but it's a trace amount. So it's an amount so small that we don't really care about it that much. So that's what we have. That's our issue, is that we want to figure out how we can figure out the mass of something, the average mass, but we also have to take into account that each isotope weighs a different amount and that it has a different abundance. So how much does a mole of hydrogen 1 weigh? Well, if we look at how many subatomic particles hydrogen 1 has, it has 1 proton. We're going to ignore neutrons because it doesn't have 1, at least hydrogen 1 doesn't have 1. And so here's what we got. We got the mass of 1 proton being 1.673 times 10 to the negative 24th grams. And we're going to multiply that by Avogadro's number, by 6.022 times 10 to the 23rd particles. And we're going to get roughly 1 gram. If you multiply that in your calculator, you get roughly 1 gram. Okay? So what we can say is that 1 mole of hydrogen 1 weighs 1 gram. So let's go on to average atomic mass. The mass on the periodic table is the average atomic mass that that atom has. So we have to go back to AMUs. So AMUs is an atomic mass unit, and it's roughly the mass of 1 proton or 1 neutron. So roughly 6.67 times 10 to the negative 24th grams. And then we have average atomic mass. So the mass of an atom taking into account the mass of its isotopes and relative abundance. So let's take a look at carbon. So carbon has carbon 12, 13, and 14. And when we calculate its average atomic mass, when we take into account how much not only each isotope weighs based on the number of protons and neutrons that it has, but also its abundance, we can see that carbon 12 weighs 12 AMUs, and that according to its abundance, it's 98.9% carbon 12. This is my abundance, and then I add that to the mass of carbon 13 times its abundance, which is like 1.06%. And then I have carbon 14, which has a trace amount. It's 1 times 10 to the negative 12%. It's a ridiculously small number. So when we do the math, we're going to see that carbon 12 accounts for this much mass, carbon 13 accounts for this much mass, and carbon 14 accounts for almost nothing, so that the mass of the average atomic mass of carbon on the periodic table is 12.01 AMUs. And that's how we get that number. So none of them individually weigh 12.01, but if we take their masses and their abundance into account, if I just take a random cup of carbon, here's what the average mass will be for all of them. Okay, and that's the number that you find on the periodic table. So how much does 1 mole of carbon 12 weigh? Well, if we go look at how many subatomic particles carbon 12 has, it has 6 protons and it has 6 neutrons. Again, each one weighs approximately 1 AMU, which is 6.67 times 10 to the negative 24th grams. So we can see that there. So what I'm going to do is I'm going to multiply 12 by the average between these two. And then I'm going to multiply that by the number of particles in a mole. So it's 6.022 times 10 to the 23rd. And if I do that, I can see that the number 12 nucleons, 12 either protons or neutrons, times Avogadro's number will give me about 12 grams. So when I did this with hydrogen, you remember 1 mole of hydrogen weighed 1 gram, and now that I look at carbon, I see that 1 mole of carbon weighs about 12 grams. And so what we can say is that 1 mole of any substance will be equal to its atomic mass, or the mass on the periodic table, in grams. Alright, so here's a question. How many carbon do you have? Of carbon would be approximately 1 carbon, because 1 carbon weighs 12 AMUs. And then how many carbon do you have if you have 12 grams of carbon? Well, that would be equivalent to its mass on the periodic table, so that would give us 1 mole of carbon, or 6.022 times 10 to the 23rd particles of carbon, which is a lot bigger number. So we have to keep that in mind when we have AMUs and grams. AMUs refers to individual atoms, and grams refers to a mole of that on the periodic table. So here's what we can say. 1 atom of something will be measured in AMUs. 1 mole of something will be measured in grams. Okay, and then that leads us to our final point, molar mass. So molar mass is the mass in grams of 1 mole of a substance. And we can find that on the periodic table. And if we have a compound, then we can add them together and figure out how many grams a mole of something would be. So if I have NaCl, I would just take the mass of Na and the mass of Cl and add them together. The units for molar mass are grams per mole, which we're going to abbreviate as grams per mole, where grams kind of go in the numerator, moles go in the denominator. And we can use molar mass as a conversion factor between moles of a substance and its mass. Hopefully this helps. See you in the next one.